Control and Information System Manager for the City of Toronto for 11 years. She then returned to school and received her master's degree in industrial engineering from the University of Toronto in 2006 and joined Ornge in early 2007, where she has been for the last 15 years. If you didn't know, Ornge is a Canadian not-for-profit corporation and registered charity that provides air ambulance and associated ground transportation services for Ontario. If you've ever seen big orange helicopters flying over the city, that's Ornge transporting patients for emergency care. As part of her role at Ornge, Mahvareh has collaborated in many process improvement and operations research-related projects with several national and international research institutes and universities, such as the School of Operations Research and Information Engineering at Cornell University, Mechanical and Industrial Engineering here at the University of Toronto, McMaster University, and Thunder Bay Health Sciences Center. Her research and professional activities are in the areas of resource allocation optimization, discrete event simulation, process improvement and performance analysis of emergency medical services, call centers, and production systems. And she likes biking, cats, and poetry. Mahvareh, take it away.
Thank you, Dionne, for the introduction, especially for the last part. And thanks for inviting me in this industry speaker series. It's my great pleasure to be here to talk a little bit about the application of optimization and simulation techniques at Ornge. So for my today's talk, I start with an introduction to Ornge to briefly explain who we are, what we do, and the scope and extent of our work. Then I introduce two optimization simulation tools that we currently utilize at Ornge and explain how they help us to be more efficient. And we'll end with discussing a little bit about lessons learned from these projects and our future work. Ornge is a government-funded, not-for-profit organization that is a vital part of Ontario's healthcare system by providing air and complementary land ambulance services to more than 13 million residents of Ontario, over 1 million square kilometers of land, which equals to the size of France, Spain, and the Netherlands combined. We transfer almost 20,000 patients across the province annually, and considering the size, extent of coverage, and complexity of work, we are the largest and most complex air medical transport system in Canada and one of the largest in the world. We have a multidisciplinary staff, including medics, transport medicine physicians, communications officers who take the calls and handle dispatch and flight planning process, pilots and co-pilots, and flight and maintenance engineers. In terms of vehicle types, we have fixed-wing aircraft for long-distance transports across the province, usually over 250 km. Rotor-wing aircraft or helicopters for medium-distance transports between 40 and 250 km, and they can also be utilized to pick up patients from difficult-to-reach locations and remote areas. And we also have some critical care land ambulance transport units for short distances, less than 150 km usually, and for complementary transports between airports and hospitals. In terms of our fleet, we have 8 fixed-wing aircraft, 12 rotor-wing, and 13 land ambulance units. These vehicles are stationed in different bases across the province. We have 7 rotor-wing bases, 3 fixed-wing bases, and besides the aircraft that Ornge owns, additional 13 fixed-wing aircraft are also available with subcontractors, and we call them standing agreement or simply SA airplanes. Compared to Ornge dedicated aircraft, they have limited availability and can only be used if the medical condition of the patient permits it. There are 5 triage or priority levels among the patients. Emergent 1 patients with conditions that are threat to life or limb, and the targeted time window for total time to definitive care for them is less than 4 hours. Emergent 2, that can be potential threats to life, limb or function, and they need time to definitive care less than 6 hours. Urgent 3 can potentially progress to serious problems, and the time to definitive care for them should be less than 12 hours. Non-urgent 4 or less urgent patients that may involve acute problems, and the time to definitive care for them should be less than 24 hours. And non-urgent calls, number 5, or we call them scheduled appointments that can typically be scheduled for next day, and time to definitive care for them is less than 48 hours. The majority of calls are interfacility transports, over 90%, and are carried out between healthcare facilities. That means a patient needs a service or higher level of care that is not available at the sending hospital. In contrast, unseen calls are direct response to the accident locations, and our operations control center works closely with 911 to coordinate and dispatch these calls. And we do them when the call meets the provincial air ambulance utilization standards. Also, modified SIN calls happen when the local land ambulance transfers the patient from accident locations to the closest helipad, airport, or hospital to facilitate the transport process. We also have a level of care. Each patient needs a specific level of care during the transportation, and it is determined by transport medicine physician according to the patient conditions, and it matches the call with appropriate aircraft and crew. There are 3 types of crew depending on their scope of practice: critical care, advanced care, and primary care paramedics. In terms of quality and research, we have a multidisciplinary team, including a small group of in-house researchers. A major part of our work includes collaborations with national and international universities and research institutes. Our main collaborators are Cornell University, U of T, Sunnybrook Health Sciences Center, Thunder Bay Health Sciences Center, and many other organizations. We scope real-life research projects and supervise student teams and trainees in many research areas, including OR and development of decision support tools. For our operations modeling projects, we've had a long-lasting collaboration with Cornell University since 2008, I believe. Specifically with Professor Shane Henderson and his group at Operations Research and Industrial Engineering Division. During this time, we were able to do some optimization modeling and create 2 decision support tools, 1 advanced simulation tool for our emergent and urgent operations, and 1 optimization tool, purely optimization tool for our scheduled next day transports. That we call them long-term planning transports, and the tool long-term planning tool. Let's start with the emergent urgent part. For this part, we have a set of requests that should be responded as quickly as possible as they arrive. The main questions are where to position aircraft and crew, and also how to track the time-dependent demand with shifts. This work has been done with different combinations of student teams, started with 2 MNG projects the first 2 years, followed by a PhD student in spring 2015. We started again in 2020 with another team of an undergrad and a PhD student to revisit the previous work. And that work is still ongoing by a current MNG team this semester. So the first project in the first 2 years was to find the optimal locations of Ornge aircraft. The goal was to improve response time as the first priority and transfer costs as the second. We did this in 3 steps using combined optimization and simulation techniques. First, analyzed the data to get some insights about demand patterns and to extract the useful part of it for our modeling purposes. Then created an optimization model to find the optimal base locations in an ideal world. And third, created the first version of our simulation tool to incorporate realistic processes and validate the tests and test the solution of optimization model. And the data shows that the hour of the day has a huge impact on the expected number of calls, and the greatest increase occurs between 7 and 11 a.m. Then we experience an afternoon peak between 12 and 5 p.m. And then from 5 p.m. it proceeds to decline. This suggests shift scheduling may impact our performance. However, as you can see in the second graph, the day of the week is not as significant of a predictor. The biggest change is from Thursday to Friday, a 5% shift in demand from that's not that significant. There are some seasonality effects too, as shown in this graph. We experience a peak demand during the summertime, and this implies a seasonal schedule may also be useful. The team formulated an optimization model using the solver Cplex that time. The objective function is to minimize a scaled combination of flight cost and response time for urgent and emergent patients. For emergent calls, we just care about the response time. But for urgent calls, cost can also be one of the considerations. That's why we decided to give 70% weight for response time and 30% for cost to have a balance between the two. As an estimation of cost, the team found the average fuel burn rate per hour per aircraft using historical data. As the parameters, we have set of possible locations per bases, set of aircraft types, and for demand side, we used 12 by 12 grids for province of Ontario, and after excluding the unpopulated areas with no recorded calls, there were around 1,000 grid cells remained, from which we could calculate the demand for scene and interfacility calls per critical, advanced, and primary level of care. Given this goal, the model was constrained by several other factors. First, the demand must be met. All calls should be serviced, which represents an ideal world and is not consistent with real operations. Second, there is a capacity on total distance flown by an aircraft over time period that should be physically possible. It cannot fly continuously and needs some time for maintenance and refueling. Third, the range constraints. That means an aircraft cannot service a call if it is too far away. Finally, the total available number of aircraft of each type should be met. There were some simplifying assumptions. All calls are serviced, all trips are triangular from base to patient, then to receiving hospital, and finally back to base. Bases can be located at any potential place, no restriction on total number of bases, and queuing effects were ignored in that optimization model. No distinction between emergent and urgent calls. All aircrafts were staffed and available 24 hours, 7 days. and only fuel cost was included in the cost function. We got the results suggesting repositioning several aircraft and crew that is not easily achievable in real life, but it could result in 15% improvements in response time and 7% improvements in fuel costs. In this map, the suggested base additions and closures are circled in red, which clearly shows drastic changes that are very unlikely to be made. But we tried to use this model to get some insights. We did some sensitivity analysis on number of aircraft of each type. And the result was if Ornge decides to add a resource, it should be a fixed wing aircraft. And to make the results more realistic, the team tried to further constrain the model by restricting some aircraft to stay where they are, or forcing to go to a nearby existing base, and did some sensitivity analysis to get some insights and produce some solution scenarios that were more feasible to work on. As the last step of this project, the team developed a simulation tool to validate and test the optimization results and run some real-life what-if scenarios. This was our first version of simulation tool, which was trace-driven. We used historical data of 2010 and 2011 for call arrivals, and just replayed the tool with these real calls, and implemented some simplified processes for call handling process, dispatch policy, waitlist policy, and not serviced calls. There were many simplifying assumptions here too that were released in next years, including availability of aircraft 24 hours, 7 days, with no shift scheduling and overtime rule in place. Availability of aircraft only at base with no preemption and no redirection from places other than base, and many others. Uniform startup time for all bases, uniform patient load and unload times for all trips. That is not real because different hospitals have different distances from their closest landing sites. And depending on distances, the patient load and unload times are quite different from hospital to hospital. In terms of platform, it was a Visual Basic application with Excel front end to enter the required input. It could step through time to handle the calls and collect statistics to evaluate the performance measures of different setups. Using this simulation tool, we ran different scenarios on base locations and number of aircraft. And besides testing the solutions from optimization model, we ran many other scenarios suggested by our decision makers to find the impact of changes. But it was a simplified model and went through several enhancements in different phases during the next years. As our second optimization modeling attempt for emergent urgent operations, with the help of a PhD student from Delft University in the Netherlands, who was visiting Cornell at that time, we worked on a more complex model for shift scheduling. He used the variant of Deskin's MEX-CLP to maximize coverage of scene and interfacility calls, subject to bounds on available aircraft and shifts. As the parameters, we had set of potential bases, demand points very similar to what we had in previous model coming from grid cells, and sets of base locations that are within the range of rotor wing and fixed wing from demand J, We also have a number of shifts per rotor wing and fixed wing, and number of aircraft per rotor wing and fixed wing. As variables, we have number of 24-hour shifts, number of 12-hour shifts starting at T, binary variables to indicate demand J is covered by A rotor wing for sync calls and A rotor wing and B fixed wing for interfacility calls. Here is the detailed formulation, which was complicated, a maximization of coverage subject to Y variables are obtained by the shift schedules. Demand J is covered by A rotor wing and B fixed wing, and constraints on available shifts and available aircraft. So in this model, when the number of shifts does not suffice to staff all aircraft 24 hours a day, the model decides which aircraft to equip with crew and at which time. With this model, we were able to do a sensitivity analysis on number of shifts. Here, we found which combination of 2 shifts of 12-hour could best be replaced by just 1 12-hour shift and what the start time for that shift should be. And we did it given the current distribution of aircraft. Also, we did the same, allowing the base redistribution, and in both experiments, the resulting shift schedules were evaluated in the simulation model. And so, to be able to do so, the second version of our simulation tool was developed. We added shifts and shift handling process to that tool, and also allowed preemption in dispatch policy and used more up-to-date data as call arrivals. And so many of our simplifying assumptions from version 1 were removed by arriving the second version of the tool. We used this version several years to support decisions on occasional aircraft relocations or aircraft renewals and shift changes, and it was good. But over time, new expectations and requirements were raised by Ornge decision makers. It was so helpful to be able to evaluate the plans for fleet renewal or relocation by this tool before making any decision. But these options, I mean, buying a new aircraft or changing the location of a base, are the most expensive and challenging solutions. They wanted to know what else we can do that are less expensive and can still make incremental improvements. For example, what happens if we change our aircraft assignment policies and use rotor wing and fixed wing aircraft just for higher priority patients like emergent 1 and emergent 2, and use SA carriers and land units that are slower for urgent and non-urgent calls? Or what happens if we change the mission profiles or our redirection and overtime policies? Is it better to redirect an aircraft every time it is possible, or just when there is no other resource available, or just for each of these questions, they need to know for different groups of patients, for example, emergent 1 patients at North, or emergent 1 patients that are transferred from hospital X. And besides the growing expectations, the version 2 that we had was only simulating our air operations with many simplifying assumptions, and land ambulance operations that was grown over time was not taken into account in that model. So considering all the new requirements and expectations, we needed a more advanced simulation tool to be able to handle all those questions. And as the result, we rewrote the tool in Python. Let's briefly explain how our new advanced simulation tool works. When a call arrives, it calculates time to definitive care in a much more accurate way than the older versions. In the dispatch software that we use in our operations control center, there is a module called short-term planning tool, or SDP tool, that we have created as part of a collaborative project with human factors group at MIE years ago under supervision of Professor Birsandanes. Using this module, we are able to predict time to definitive care more precisely using an interval-based approach and some statistical modeling out of historical data. Intervals include the entire process in detail, from time 0, when Ornge receives the call, up to transfer of care at receiving facilities. And it takes all location-related details into account. For example, for the interval from the time medics and patients depart the sending facility to the time they arrive at the close-by sending landing site, where the airplane is waiting for them. This time will be calculated based on distance between the landing site and sending facility, and whether or not it involves a complementary land transfer for this purpose. So we have much more accurate time estimations, and after time estimations, the tool starts ambulance search to find the feasible resources based on the deployment rules. For this part, we have included the mission profile maps, exactly the maps that are utilized in the dispatch software, to find whether the call is feasible to be assigned to a resource or not. And after checking the feasibility of each resource, the tool creates a set of feasible assets, and then it generates a preference order among them. The preference order is built based on the defined deployment rules for different combination of type and priority groups. And for all different combinations, we have the preference order, and these are the sections of the code that are very well documented and written in a way that can be changed easily for any alternative deployment rules for doing what-if experiments on deployment rules. In the set of visible assets, if it's not empty, the tool assigns the first asset based on the preference order. Otherwise, the call will be waitlisted. When the tool assigns the asset, it moves forward to the other stages of the journey based on the estimated interval times that we find from the SDP tool. At each stage, the location of ambulance will be updated based on that interval. Here it's depart base, arrive at sending, arrive at receiving, patient drop off and depart receiving, and finally return to base. And there is a stat collector object here that collects the data of patient journey in all stages. When there is no available resource, the call will be placed in the wait list. There are 2 waitlist checkpoints. First, after patient drop-off at receiving location before getting back to base. And second, when an ambulance becomes available at the beginning of a new shift. The waitlist is checked based on the order from highest priority to the lowest. And among the same priority levels, we have first come, first serve rule for now. In reality, the transport medicine physicians triage among the same level priorities, but we have not this implemented in the model yet. We have validated this tool using historical data. We used 3 months data to compare real versus model results, given the real settings that we had in that period of time. We did a resource match for the assigned assets and compared the percentage of compliancy in each priority group based on the targeted time windows that I explained for each priority group. 4 hours for emergent 1, 6 hours for emergent 2, etc. And as you can see here in this table, the results are amazingly close. It's, I guess, because of including very fine details in this tool. These days, we are using this tool quite frequently to do what-if experiments to support our performance improvement initiatives. There is a precision dispatching committee at Ornge who are responsible to modify deployment rules to improve performance measures, especially for emergent 1 patients. This application is a vital tool for them to support their decisions these days. Now, I believe we can move to the second tool, which is a purely optimization tool for non-urgent scheduled patients. For this part, we receive the calls during the day, usually until 5 p.m. We'll take them all together and schedule for next day based on aircraft availability, patient requirements, and some other conditions. And we typically have 10 to 20 requests of this type per day. In past, before we touched this problem, the route planning was highly dependent to planners' experience. They had a very old MS-DOS-based application called Aerosoft that could be used to find the transport costs for a given route, but it had nothing to do with optimization of routes. So the key problem at the core of Ornge mandate was how to schedule and route available airplanes at minimal cost. There are some opportunities for optimization practices for this group of patients. First of all, unlike the emergent urgent group that should be responded as quickly as they arrive, we have enough time to plan in advance more thoughtfully and efficiently for this group of patients. Also, it is possible to transport patients in groups. We can transport up to 4 patients in each trip, and we can also group patients on each leg, depending on capability of aircraft and patient's condition. So there are rooms for optimization practices here, but the problem is complex. We scoped a project to develop a tool to support route planning and flight scheduling decisions on a daily basis. So the goal was to improve transport costs. These are non-urgent patients, and to decrease the human-related variability. In terms of functionality, the tool should be able to accept input data on patient information, origins, destinations, the scheduled times, aircraft availability, and some other required parameters. It should be able to formulate optimization model based on these parameters and find the optimum solution and present the results as output. And the underlying mathematical problem here is a static dial-a-ride problem with non-homogeneous vehicles and multiple depots. The formulation is based on set partitioning, integer programming, minimization of cost subject to responding all requests and availability of aircraft. Here is the number of variables or generated columns, given the fact that we consider we can transfer 1 to 4 patients in one trip. And this is an upper bound because some combinations are infeasible and will be omitted from the formulation. And here are the parameters. The heart of the parameter, the problem here, is how we calculate the cost coefficient vector C. Cj here represents the minimal cost of handling the requests of column J using the associated plane. Since the requests can be handled in any order, subject to certain time restrictions for patients pickup and drop off, for a subset of K requests, we need to consider all K factorial orderings, and within each ordering, we need to generate all possible routes given the sequence of pickups and drop-offs. This slide shows an example of route generation tree for a column of 3 requests, including patients 9, 10, and 11. The locations are S9 for patient 9 pickup location, T9 for patient 9 drop-off location, and so on. If we start with S9 here, the next possible locations can be S10, S11, or T9. And if we start with S9 and then S10, since the maximum capacity of airplanes are 2 patients, it cannot be S11, but it can be T9 or T10, and so on. It goes on in each branch to generate all possible orderings. Here is the enumerative algorithm that we have. We first generate all possible subsets of request pool, and within each subset, we generate all possible routes, as I showed you. The feasibility of each route is evaluated using the site constraints that are, in fact, are real-life constraints. And among the feasible routes, the cheapest one is saved for each subset. So we can have C vector from these algorithms. For the first version of the tool, we considered a simplified objective function for total cost with just considering the charter cost based on the charter fee of subcontractors and fuel cost. And as the site constraints, we implemented plane capacity based on the number of stretchers that they have. Duty shift constraint, which means total time taken for a round trip must not exceed 13 hours. It should meet appointment times of patient, and level of care required by patient should also be met. So. And the developed tool has 3 layers: a user interface, which is Excel here, the formulation core to formulate the problem using the inputted data, and the solver. In our first version, we used Ample for formulation core, and as the 3rd layer, we have optimization solver, and for that solver, we used an open source at that time. We tested that first version, and the results were a bit terrible. Although the results were cost effective, they were so unrealistic and sometimes quite funny. And it was due to not taking many of real-life constraints into account. The tool had a very, very long runtime too, over 40, but the potential cost savings was convincing enough to continue and refine the tool during the next years. Solution platform by moving to C++ for the formulation core. And also we switched to Garubi as the solver. With this new platform, we've had a huge improvement in runtime. Now for problems between 10 to 20 requests, it takes less than 1 minute. For 20 to 25, less than 5 minutes. And for over 25, around 7 minutes. Cost function was improved over time by using more actual data for fuel burnt estimations and fuel cost. Also added some new elements to the cost function like detention cost, which is the cost per hour in excess of the first hour that airplane remains on the ground. And the vital part was implementation of more real-life constraints to those site constraints in enumerative algorithm. The more real-life constraints we added, the more realistic and workable results we got. And so the trust to this tool started to grow in next versions. And we implemented all these real-life constraints over time, each one by a specific MNG team or PhD student. This type of tools need careful validation and assessment. We went through this through several experiments in several phases. In our first experiment, which was a retrospective analysis, we took 50 sample days between July 2010 and February 2011, retrieved actual schedule flown from historical data, and ran the tool to derive the optimized plan, and calculated the costs using the tool's cost calculator, and the results was showing 16% improvement in total cost during that period of time. In our second experiment, we did a prospective analysis. We worked with one of our most experienced planners, and during 2 months in summer 2012, we randomized the days to application use versus manual use and compared the outcome. And the results was showing 7% improvement in average costs per average required distance during that period of time. In another assessment in summer 2017, besides the cost efficiency, we assessed the adherence and dependency of our scheduled trips to the optimized plans. So over 2 months, we monitored the tool's utilization, and for each plan determined whether it was derived from the tool or it was planned manually. We then compared the plans with the next day's actual trips and categorized each trip into exact, minor deviations and major deviations from optimized plan. The cost comparison of these categories once again proves the cost effectiveness of tool-derived plans. But besides the cost evaluation for those major deviations, we also found the common reasons for manual modifications, which is primarily addition of last-minute requests that Ornge receives after 5 p.m. when the planners have already completed the planning tasks and organized everything with SA carriers and local ambulances. The problem is that when they rerun the tool with the new set of patients, sometimes it changes all the trips, including the ones that have already been organized. So it's very difficult and kind of impractical to change the organized trips. And in such cases, they make some manual changes in the parts that are flexible to change. Some other reasons that usually happens during the next day's operation are aircraft failure, weather problems, and preemption by emergent calls. The results of this evaluation has drawn our future roadmap for enhancement of this tool. We first need to integrate the tool with the dispatch software in our operations control center to first make it easier to use by our planners, because everything is inputted manually by them in this standalone application. Also make it possible to exchange data between the two applications to update the status of the trips after they are planned and during the operations next day. And then to create a schedule repair side tool that can connect to dispatch software to update the status of the planned trips and initialize the parameters at the time of change to reformulate and re-optimize based on the new setting. I believe I'm done regarding the explanation of the two tools, and let's talk, if I have time, a little bit about lessons learned.
I think we could do another 5 minutes because we could go over time by max of 10 minutes. So, yeah.
Okay. No, I think I can tell this in 5 minutes.
Okay, sure.
Okay, perfect. In terms of lessons learned, first of all, the collaborations between industry and universities are truly win-win. Students can be exposed to first-hand real-life projects, and industry can be benefited hugely from the results. For the long-term projects that take more time than the life cycle of a student project, which is typically a few months for a course project, or 1 year for capstone or other types of projects, we need to carefully break down the projects in a way that are doable by different student teams in a long run. And these projects should be very, very well documented to be able to continue the work with other teams. For such decision support tools, as I explained, we need to spend a good amount of time for validation of these tools to convince the end users and decision makers to trust the tools and use them. I believe this part is much more challenging than development of the tools. And we also need to consistently evaluate these tools to ensure about their proper utilization over time and build their future roadmaps. As the future work for the advanced simulation tool, we are still working to add more fine details and some visualization features to the tool. And as I said, we are working with a current image project this semester for this tool. For the long-term planning optimization tool, we are working on integration and integration with our dispatch software in operations control center, and to develop the schedule repair site tool. Also, we have just started a new collaboration with U of T, with Ornge Golestanian and Professor Chris Beck for optimization of shift scheduling, with more focus on remote northern communities and modeling paramedic hiring problem, which is an untouched area in our initiative so far. And at the end, I would like to acknowledge Dr. Russell McDonald, our former medical director, who was project champion in these projects during 15 years ago. The staff of Operations Control Center for their support, cooperation, and patience, especially during the testing phases. Professor Shane Henderson and Professor David Schmois for wonderful guidance on academic side, and over for the graduate students who work with us from 2008 to now. And that's it for me. Thank you for listening.
Thanks, Mahvareh. That was a fantastic talk. It's great to see all the different analytics tools that you're able to bring together and then actually have an impact on real healthcare problems. That's definitely something that we don't always get to enjoy in a pure academic sense. So there are a number of questions from the audience. So I'll relay them to you. So first, Behruz asks, when it comes to simplification for the purpose of modeling, which models were more simplified, mathematical models or simulation models?
Mathematical models, because in simulation, we have more flexibility to implement as many as real life complications that we have. It just needs time and to recognize them very well and to decide to implement which one that has the most impact on results. But for sure, for the mathematical part, we have more limitation in terms of implementing the very fine details of real world problems. But at least I think the long-term planning tool that I explained, because of the algorithm that I explained and the opportunity to have that side constraint part, we were able to make it as close as possible to the real life operation. I can say this is a purely optimization model, but it generates very good plans. And the reason that some of our plans have deviation from the tool, as I explained, it's not because of not taking the real life constraints into account. It's mostly because of the limitations of operations. They cannot change the plans that they have already organized. It's very impractical. And we need just to make it feasible for them to identify which plans are flexible to change and just to reformulate and re-optimize the plan for them.
So Behruz also asked, why did you not use a special focused simulation application?
That you mean why we used a Python? It's mostly the choice of the academic side. We at industry we can just tell them it shouldn't impose many costs to us. As you see, we have done all these projects with minimal costs, and the only cost that we had was buying the license for that Garubi software. And Python is free of charge. We were able, and I believe they had more flexibility in Python to develop the very fine details of operations research. And it's mostly the choice of the academic side. And our experience was pretty well with this configuration.
And then Behruz had one additional question. Did you use SymPy for the DES, or did you create your own model without any external packages?
Combination, I guess. We did the both. For some parts, we developed ourselves.
Okay. So Benji says, love your work. You mentioned potentially adding land ambulances. What are the current ways that land ambulances are already considered in current decision-making?
Land ambulances, especially in southern part of Ontario, can do a lot regarding the transfer of our non-urgent interfacility calls. And we had not considered them in our original model because we were focused on air operations. But over time, after refining the deployment rules, the operations of land ambulances were grown because it was better to save the rotor wing and fixed wing aircraft for more higher priority patients, and use land ambulance and SA carriers that were slower for non-urgent parts. It was not the same in past. These changes were made over time, and this way the operations of land ambulances were grown, and at that time that we were revisiting the tool, we understood that we should add the land ambulance operations into the model to have a realistic one.
So next, Hamed has a couple of technical questions. First is, was there a particular reason for switching from CPLEX to AMPLE? And also, if Gurobi is used as a solver option in AMPLE, do you know why you got different results?
I think, again, these questions can be answered best from our technical academic partners. But for switching from that, it was because the runtime improved very much when we had the Gurobi solver and our own license compared to the open source. And C++, I guess it was not just the matter of changing the platform, moving from AMPLE to C++. There were some inefficiencies in the codes that the Eng team had created too. Maybe if they were working and they could address those inefficiencies in AMPLE, we could get the same results, but it was their decisions to move to C++ and do that. And as I told you, we at industry don't say that much about their technical selections.
And then Hamed's second question is in the enumerative algorithm slide, so the one where you had the horizontal tree, when constructing the tree, if S9 goes to T9, the bottom branch, wouldn't we have the option to pick up 2 patients again as the capacity resets to 0 once the vehicle gets to the drop-off location? So.
Oh, here we show for just 3 patients. So if we go through a subset of 4 patients, for sure, we see the capacity of 2 patients per branch.
Okay.
Here we went through a subset of just 3 patients. So we have already picked up a patient here, and we can add the second one here after we have dropped off one of them, because we can't have 2 patients at the same time on airplane. Okay.
Okay, so Aaron Lamb, who I should say works at Air Canada, so definitely he's got a question thinking about how to apply these same approaches for himself. He asks, specific to delays related to airport and ground operations, how are those quantified / considered in the model?
Yeah, a very good question. As one of the parameters, I can explain this in both tools. For our emergent urgent parts, as I showed you, we have all the intervals, and we calculate one of the intervals are transfers from airports to facilities and vice versa. For that, those intervals, since we calculate the estimated times based on our historical data, all those delays are incorporated in the calculations. This is what we have in emergent urgent part. In our long-term planning also, one of the parameters that we have is turnaround time at airports. So for each airport, again, using historical data, it's based on the airports. In the first version, we had an average turnaround time for all airports. But we recognize this problem because different airports have different types of delays. And we tried to find those turnaround times per airport from our historical data. This is how we incorporated this as parameters in the tool. And even besides that, it's not just airport delays. For example, if we transport one infectious patient in one leg, as the turnaround time and the time of next takeoff, besides the delays of airport, we need to consider the decontamination time too after we want to pick up another patient after we already dropped off an infectious patient. We have all these details into account in the tool.
And also, what is your recommendation on building trust in these kind of tools in day of operations? That's definitely always a tricky one.
Consistent evaluation. You shouldn't leave the users on their own. All of these tools need consistent evaluation over time. As I told you, it gives you some ideas how they are using the tool. Is it appropriate and in the expected way? And also it shows you the future roadmap, and it should be consistent. It should be, you should go through this several times during the life cycle of tool. And validation, again, validation is a very important part of the model. We shouldn't simplify that phase. For the validation part, they really need to trust the tool, and because they want to rely on the results of these tools for our very sometimes strategic decisions on base locations, on buying a new aid. These are not simple decisions. They have right to trust these tools, and we need to put some good amount of time for these parts of the project. Some people think that the development of the tool is the end of project, but no, I believe it's just the startup project.
Yeah, absolutely. Absolutely. I think that's a really good way to look at implementing these real world tools, especially when stakes are very high, like patient health, right? The tool itself is just step one.
Yeah.
Okay, so there are 4 more minutes left, so we'll have time for maybe 1 or 2 more questions. So the next question is from Davison. For the urgent planning Python simulation approach, could you further describe how the tool is used? Who uses it? That is technical staff with an OR background or dispatchers with other types of backgrounds? And when, how often is the tool used?
It's me. For long-term planning tool, we have our planners working with the tool, and that's why we have a lot of challenges for that part. But the simulation tool, its only user, the only user is me so far, but we can include some other technical staff again, because the person who works with that tool should know simulation, should know how to change some Python codes if we want to run different scenarios. And it's a little bit more technical, I hope. And in terms of frequency, it really depends on at which stage the organization is. Now, since we have a task force for process improvement of our deployment process, it's very frequently 50% of my time is spent with this simulation tool. But when we are done with this task force, it's less frequent. It really depends from time to time.
Yeah, So Robert asked a related question, and I'll ask you if you could maybe be brief, because there's one more question that I want to squeeze in after that. So Robert says, thanks for an inspiring talk. You mentioned documentation is crucial for continuing the projects. Can you share advice for how to manage and perform this documentation?
I can send you some samples. This is the part that, again, our academic partners are taking care of. I can show you some samples. Don't have it ready here right now, but I can just say that well documentation is a very crucial part of the work in such projects. When the project ends after working with one group, it's okay. But when it should be continued by other teams, you need to have a very well-defined documentation. For these tools, we have very good comments in the code, and we have some documents development that is used by developers to continue the work. I think the technical staff should be very knowledgeable about how to document these projects very well.
All right, I want to squeeze in one more because I also have this question, and then we've got to run because it is 12:10. That means it's U of T time for other meetings to start. So Arnusha asks, I was wondering, has COVID-19 impacted the use of any of these optimization or simulation tools?
Very good question again. Since our intention was to decide to make the decisions that are related to our normal operations, we decided to exclude the data of after March 2020 because it could make the results skewed because of COVID workload that we had. It was possible to do some occasional analysis for specifically the purpose of COVID-related decisions for especially resource assignments. But in majority of time, we have excluded the data of COVID time because the intention for this model is to make adjustments for our normal operation.
All right. All right, Mahvareh, thank you so much for an absolutely amazing talk. It was great to see you. So just so everybody here knows, Carte offers an entire seminar series, and Samaya has posted a link where you can see upcoming talks and register for them. And I hope you all enjoyed today's presentation.
Thank you.
Thanks a lot. Thanks a lot, Mahvareh. Thanks a lot, Professor Aleman. This was a great seminar, I'm sure you can say, because everybody is still hanging around. Hope to see you again in the future. Bye.
Thank you so much.
Bye, everyone.